Good morning, children. So let us continue our chapter, units and measurements. And this is the last topic in that chapter, dimensions. Okay. So in the last session, we studied about the significant figures. What are significant figures and what are the rules we are following to fix the significant number of significant figures, and what is the rule we are following to round up the number, isn't it? These are the things we discussed in the last video. Now we have to study about dimension. This is one of the important session in this chapter, and in whole physics we have to know about dimension. So what is dimension? Dimension is the representation. It is a representation. And what we are representing? We know physical quantities. It is classified into two. Which are they? They are fundamental and derived. Fundamental and derived quantities. And how many fundamental quantities are there? There are 7 fundamental quantities. And we know that all the derived quantities are coming from this 7 fundamental quantities. So dimension is a representation which gives the relation between the derived quantities and fundamental quantities. How derived quantities are related with the fundamental quantity, that relation we can represent in terms of dimensions. That representation is known as dimensions. So basically all the 7 fundamental physical quantities are having the dimensions. So we'll relate this derived quantities with that fundamental quantity and we get a representation, and that representation is our dimension or dimensional formula, or we can call it as the dimensional equation. Okay, just writing the relation, we'll call it as the dimensional formula. And if we are equating it with the fundamental derived quantity, that's the physical quantity, we'll call it as the dimensional equations. Okay, so first we have to study what are the dimensions of the fundamental quantities. So you know there are 7 fundamental quantities, and which are they? We know it is mass, length, time, temperature, electric current, amount of substance, and luminous intensity. So all these quantities having a representation, and we'll relate the derived quantities with this fundamental quantities. Okay, so the dimensional representation for the fundamental quantities, this dimensional representation, we'll write it inside a square bracket. If you are writing the quantity or the representation inside the square bracket, that is the dimensional representation. So we know the fundamental quantities are, I'll write it, fundamental quantities are mass, time, length, temperature, amount of substance, electric current, and the last one is luminous intensity. Okay, luminous intensity. So for this 7 fundamental quantities, there are having the dimensional representation. Okay, so first we can write for mass. For mass, the dimension of mass is represented by capital M. So here to represent the dimension, we are using the capital letters and this capital M, and it is represented inside a square bracket. So this is the dimension of mass. Okay, and what will be the dimension of time? Time, it is represented by capital T inside the square bracket. What is the dimension of length? Yes, it is capital L inside the square bracket. Okay, so the dimension, it is the representation, dimension represent in the square bracket. Okay, so for mass it is m, time is this capital T, length it is capital L, and it is represented inside the square bracket. So what is next? Next is temperature. So the dimension of temperature, it is K, that is Kelvin. Unit of temperature, it is Kelvin. So it is K, and amount of substance, it is mole. Okay, unit is written in the square bracket. And electric current, it is ampere, that A in square bracket, and luminous intensity, what will be that? CD inside the square bracket. Okay, CD inside the square bracket. So these are the dimensional representation of all the fundamental quantities. Okay, dimensional representation of the fundamental quantities. So what is it? Dimensional representation means it is the representation, we are representing it inside a square bracket. Okay, and using this we can relate all the derived quantities with the fundamental quantities. Okay, so next we have to discuss that. So you write down the next question. What do you mean by dimension? What do you mean by dimension? Write down all the derived physical quantities. All the derived physical quantities are related with the physical quantities can be expressed. All derived physical quantities can be expressed in terms of some combination of seven fundamental or base quantities. All these fundamental quantities are the seven dimensions in the world. And it is denoted inside in the square bracket. The seven dimensions are, then you copy this. Okay, the seven dimensions are mass, time, length, temperature, amount of substance, electric current, and luminous intensity. That is the seven fundamental quantities. And the dimensions are here. It is m inside the square bracket, T, L, K, mole, ampere, and candela inside the square bracket. Okay, so that is about the dimension. Next, we have to discuss about the dimension of a physical quantity. So what is the dimension of a physical quantity? Dimension of a physical quantity is the representation, that is how much power a fundamental quantity must be raised to represent a physical quantity completely. That is known as its dimension of a physical quantity. Okay, so I'll explain with an example, then it will be clear. So here, a simple one we can take, that is density. You know, density is a derived quantity, isn't it? What is density? Density is equal to mass by volume. Isn't it? Density is equal to mass by volume. That is, again, mass, it is a fundamental quantity or the base quantity. And what is volume? Volume is L cube, isn't it? It is equal to L cube, length into breadth into height. So it is the measurement of length, product 3 times. So it is equal to L cube. Everything is length, isn't it? length, breadth, height. So all the measurement are length. So we are writing it as L cube. Isn't it? Length cube. Length cube. So see, density is a derived quantity, and that derived quantity we got it in terms of the fundamental quantities, that is the base quantities. What is it? Mass and length. Okay. Then we have to represent the dimension of this. So dimension of mass, you know how much it is. Dimension of mass is, what is it? Capital M inside the square bracket. By length. What is the dimension of length? It is L. And how many L's are there here? 3. Yeah. So L cube. And we won't write it like this. We will write everything in a single, that fractional method we won't use. So we can rewrite it as M, and this L cube we have to bring it in the numerator, that is L. 3 comes here, minus 3, isn't it? And we can put it in a single square bracket, that is M L minus 3. ML minus 3, close the bracket. So what is it? This is the dimension of which physical quantity? Density. Okay, dimension of density is ML raised to minus 3. We will read it as ML raised to minus 3. So after looking this, it is very clear, isn't it? What is it? It is depending upon mass and depends upon length. And how it depends? So it is very clear from the dimension. Understood? So dimension of a physical quantity is to what power we are raising the dimension of the fundamental quantity. That is known as the dimension of a physical quantity. And in general, we will represent the dimension in terms of M, L and T. All the three, that is mass, length and time, that we are considering as the basic. So mass, length and time. So here mass, length is minus 3 and time is not there. So in such case, we will write it as T0. So what is T0? A raised to 0 is 1. So no change in that. So this is the method of representation. General notation is like it is in terms of all the three, that is mass, length and time. If you are not writing that also, no problem. But this is the general criteria. That is all. Okay. So if M is not there, you have to write M raised to 0. L is not there, L raised to 0. T is here. In density, T is not there. That is time component is not there. So T raised to 0. Okay. So this is the dimension of density. So we can discuss one more example. We can take velocity. Yeah. Velocity. Velocity is a derived quantity. What is velocity? Velocity is equal to distance divided by time. Isn't it? Distance divided by time. So distance is the measurement of length. So we have to write the dimension of length, that is L. By what? Time. What is the dimension of time? It is T. Isn't it? So that we can write L T raised to, here it is 1. So coming to numerator is minus 1. Make it in a single bracket. L T minus 1. So M is not there. So I am writing M raised to 0. Close the bracket. So what is the dimension of velocity? Is M0 L T minus 1. Or you just say L T minus 1. Understood? So that is the dimension of velocity. Understood? So writing like this, that is known as the dimension. That is relating all the derived quantities with the fundamental quantity. See, the velocity, it is depending upon the fundamental quantity, length and time. Okay. So one more example, that is, what is it? We can take force. Yeah. What is force? Force is equal to mass into acceleration. Isn't it? Force is equal to mass into acceleration. So mass, we know directly it is a fundamental quantity. So mass into acceleration. What is acceleration? Acceleration is velocity by time. Again, what is velocity? So we have to bring it in terms of the fundamental quantity. Velocity is distance divided by time into time. So then velocity, distance by time, and already one time is here. Now look at the equation. It depends upon mass, fundamental quantity, distance, that is length, fundamental quantity, time, again fundamental quantity. So how can we write the dimension of mass, m, isn't, and dimension of distance, that is l, and dimension of time, t, and one more t is the t, like 2 times other. So tt. So what is it? M, L, what is t into t? That is t square. So coming the numerator, it is t minus 2. Isn't it? Make it in a single bracket, that is m, L, t minus 2. So here m, L, t, all the terms are there. So it is m, L, t minus 2. Understood? So that is the dimension of force. Dimension of force is m, L, t minus 2. Clear? So this is the method of representing a physical quantity as its dimension. Okay, so write down the next question. Write down what do you mean by dimensions of a physical quantity. What do you mean by dimension of a physical quantity? Explain with an example. Explain with an example. Dimensions of a physical quantity are the powers to which the fundamental quantities must be raised to represent that quantity completely. Okay, to represent that quantity completely. So you write example is a density, not this force, because density is the simple one. So here so many other things are coming. Yeah, so many. So first we can write the example for density. So you write this, density is equal to, example, mass by volume. So it is equal to mass by length cube. So what is it? M L cube, that is M L. This power we will write outside the bracket, minus 3 M L minus 3. So what is the power? That is the question. Here, what is the power of mass? All other things are same, isn't it? We have saw the example. In all other things, everywhere M, L and T is coming. Only the difference in the power. So here the power of mass is 1. Power of length is minus 3. And power of T is, what is it? M, L minus 3, T 0. Only the powers are changing. All other things are M, L and T. Okay. So this is the example for dimension. So there's dimensions you have to derive and you have to study. Okay. No need of by hearting. If you know the trick how to find out, if you know the relation. Okay, relation between the physical quantities, you can derive the dimensions. No need of by hearting everything. Understood? For 2-3 examples you can write. So write down the next question so that you try to do that. I explained already. Derive the dimensional equation for velocity velocity, acceleration, velocity, acceleration, force, force, work done, work done, momentum, work done, momentum. So work done and momentum also I'll explain. How will you find out? So what is work done? So that is what we told you to study the equations. 9th standard. 9th standard you studied work done. What is work done? Force into displacement. Force into displacement. Force we know. What is force? Mass into acceleration. Into displacement. Isn't it? Force we already derived. Again I am explaining. So acceleration is velocity by time into displacement. That is mass into velocity is distance divided by time. Length by time into second. Then write the dimension. Mass it is m. Length it is L. Time it is T. Sorry, distance again. Sorry, not S. It is distance. It is L. Then time it is T. And one more T. T into T is that. So what is the power here? M raised to 1. Then L. So it comes L 2. Then T square. So it comes up T minus 2. Close the bracket. So what is that? M L raised to 2 T raised to minus 2. That is the dimension of work done. Okay. So 1 mass, 2 length and 2 time inverse. Okay. So that is the dimension equation for work done. ml square T minus 2. Okay. Then if you know this, we can write down what is power. What is power? Power is W by T. Work done by time and power. So already the dimension of work done we have. What is it? M L square T minus 2. Again what is coming? One more time is coming. That is T. So what is it? M L square T comes here minus 1. So minus 2 plus minus 1 it is minus 3. So what is the difference? Here T raised to minus 2. Here it is T raised to minus 3. Power has changed. Okay. Everything is in mass, length and time. Okay. So this is the dimension of power. So next is a homework question. So you write down the question. Write down the dimension of or derive the dimension of energy, momentum, pressure, energy, momentum, pressure, impulse, electric charge, time period, frequency, Okay, time period, frequency and gravitational constant. Time period, frequency and gravitational constant. Okay, so you try to do that. if you are not getting, I will explain you in the next class. Okay, so very simple. If you know the equation, you just write it. Okay, and find out what is the power of the quantity. Okay, exponential of the quantity. So that representation, it is the dimension. Okay, so gravitational constant, that is the only thing, it is a little bit difficult. So in the gravitational constant, how will you write? I will give you the hint here. Gravitational constant. So did you study the gravitational constant? The gravitational force, F is equal to G m1 m2 divided by r square. So here in this equation, force you know, mass you know, and r is the distance. So G, what is it? G is equal to Fr square divided by m1 m2. Then write the dimension of this force, distance, mass and all. Then simplify. Okay, so you will get that dimension. Okay, dimension of the gravitational constant. You try it. If you are not getting, I will tell you. Okay. So according to the dimension, physical quantities are classified as dimension, dimensional constants, dimensionless constant, dimensional variables, and dimensionless variables. That is, some physical quantities are constant. That is very few, and majority are variables. Isn't it? Force, it is a variable quantity. Velocity, it is a variable quantity. Isn't it? So according to the dimension, it is classified into dimensional constants, dimensionless constants, dimensional variables, dimensionless variables. So what are they? So dimensional constant. So in the last example, what is it? Gravitational constant. It is a constant, isn't it? Gravitational constant is a constant. And I told you to find out the dimension. So it is a dimensional constant. Velocity of light, speed of light in vacuum. What is it? 3 into 10 raised to 8 meter per second. It is the velocity. It is having the dimension. So such quantities are known as dimensional constant. Okay, quantities which have the dimension. Then dimensional less constant. Dimensionless constant. So what is that? They are constants, but they don't have dimension. That is, they don't have unit. Isn't it? They don't have unit. Can you tell me one example for that? Last year you studied in the chapter light. You studied about the refractive index. Isn't it? Refractive index. It is a constant for a particular medium. It is a constant. Is it any unit for that? No. It is the ratio between the velocities. It is not having the unit. Therefore, it is a dimensionless constant. Okay. Relative density. Density of a substance with respect to density of water. So it is also not having the unit. So it is also a dimensionless constant. Isn't it? So dimensional constant and dimensionless constant. Then what is dimensional variables? Yes, it is a varying quantity. Like force, it is a varying quantity. It is having the dimension. Velocity, it is a varying quantity. It is having the dimension. So such quantities are known as dimensional variables. Then dimensionless variables. Variables which does not have the dimension. So what is it? One example. Ankle. Isn't it? So that dimensionless variables. Variables which are varying quantity, but it does not have the dimension, or it does not have the unit. So what is it? Angle is an example for dimensionless variable. Okay. Strain is, you will study in the next chapter, not next chapter, part 1 2 textbook. First chapter you are studying. Strain is the ratio between the change in dimension. So it is a variable quantity, but it does not have dimension. So it is the dimensionless variables. Understood? So write down the next question. Define dimensional constant, dimensionless constant, dimensional variables, dimensionless variables with the examples. So write what is it? Dimensional constants, physical quantities which possess dimension and have constant values. Gravitational constant, velocity of light, etc. Examples. Then dimensionless constant quantities having no dimension. Refractive index, pi. Isn't it? What is the value? It is 3.14. Is it have any unit? No. So it is a dimensionless constant. Then dimensional variables, physical quantities which possess dimension and have variable values. Example: area, volume, force, density, time, many other. Dimensionless variable, physical quantities which have no dimension but have variable values. Angle, specific gravity, strain, etc. are examples. Okay, so study this. So next we have to discuss about the applications of this dimension. Okay, we have the dimension, and from that we know the relation between the derived quantities and the fundamental quantities. And what is the use? Why we are going for this dimension? There are 3 applications are there. Out of 3, you have to study only 2. I'll tell you what are the 3. First one is, if you know this dimension, or based on the dimension analysis, we can convert a physical quantity from one system of unit to another. Okay, one system of unit to another. For example, we know the physical quantity in CGS system, that is force. Okay, force we know in CGS system, that is gram per centimeter. Gram per centimeter per second. Okay, that is a unit will come. Force unit, you know, it is Newton. Or length, for example, simply length. In CGS system, we know length unit is what? Centimeter. And we can convert that into SI. In SI, what is the unit of length? It is meter, isn't it? So we can convert it into what? Meter in SI by using the dimensional analysis. That is the one application. So from one system of unit to another system we can convert. Okay. Then the second application is, if you have a physical relation. Okay, a relation is given, a physical equation is given to you, and you can verify that is it correct. That is, LHS and RHS are equal. Okay, if a person is saying that force is equal to mv, mass into velocity. Now you know it is not correct. That is force is equal to mass into acceleration, isn't it? We have studied that. But one person is saying that, thus initially one person is saying that force is mass into product of mass and velocity. So that you can verify. Is it like that? By checking the dimension, okay, or doing the dimensional analysis. Okay, that is the second application. And the third one is you can derive a physical equation. Physical equation for a physical quantity. Derive an equation for a physical quantity if you know on which are the factors. What are the factors on which that physical quantity depends? Okay, the same example you take, that force is equal to mass into acceleration, m into a. So you know, now you know it is the product of mass and acceleration, isn't it? So that you can derive, it is product of mass and acceleration. It is not equal to m plus a, or it is not equal to m minus a, or it is not equal to m by a, or m raised to a, anything. It is equal to mass into acceleration. Okay, a person is saying that force depends upon mass and acceleration. Force depends upon mass and acceleration. So depends means many ways are there, like maybe I told you mass plus acceleration, or mass minus acceleration, or mass divided by acceleration. So you can find out it is mass into acceleration. Force is equal to mass into acceleration on the basis of this dimensional analysis. Like that, anything. Okay, this is just an example. So these are the applications of dimensional analysis. What are they? We can check the correctness of the given relation. We can derive the physical relation between equation for the physical quantity. If you know which are the variables it depends, then we can convert a physical quantity from one system of unit to another. Okay, so this one you don't want to study, that is conversion of physical quantity from one system of unit to another. It is not required for you. So the other two you have to study. Okay, so first we can discuss how can we check the correctness of a given physical relation. So before that we have to study principle of homogeneity. Principle of homogeneity. Principle of homogeneity. It states that, principle of homogeneity states that if you have a equation, dimensional equation, then according to the principle of homogeneity, the powers of the equation, powers of the dimension in that equation will be equal on both sides. Okay, that is known as principle of homogeneity. That is, for example, here we have AB, A raised to n and B raised to n. That is on LHS. And in RHS, you have A raised to x and B raised to y. Okay, so according to principle of homogeneity, n is equal to x and m is equal to y. If it is not equal, what is it? This relation is not an equation. Okay, it is not an equation. Here it is not equal to this. If it is equal, powers of the dimension A, here the power is n and here the power is x. So n and x will be equal. And here it is m and here it is y. M and y are equal. So based on this principle of homogeneity, we are going for the applications of this dimensional analysis. Okay, so write down next question. State principle of homogeneity. State principle of homogeneity. Principle of homogeneity. According to this, a physical equation will be dimensionally correct. A physical equation will be dimensionally correct if the dimensions of if the dimensions of all the terms, if the dimensions of all the terms occurring on both sides of the equation, occurring on both sides of the equation are the same. Both sides of the equation are the same. Okay, so that is the principle of homogeneity. Okay, so this is the next question, that is the first application of dimensional analysis. How can we check the dimensional correctness of a physical equation? Explain with an example. Okay. So, I will explain it with an example. That example is very common to you. We studied in 9th standard. That is, we are taking the equation S is equal to ut plus half at square. S is equal to ut plus half at square. Okay, you studied this. You know what are the variables represent. What is S? S is the distance, isn't it? Displacement. U is the initial velocity, T is time, A is the acceleration, again T is time. But here what is it? LHS, it is distance, isn't it? Or displacement. And in RHS, what are the things? Isn't it? Equation we are taking as LHS and RHS. This is the LHS and this is the RHS. So here no length, isn't it? No displacement is there in RHS. Here only velocity is there, time and acceleration. And it is saying that this is equal. So we have to verify on the basis of dimensional analysis. So we can write dimension of LHS. Isn't it? Dimension of LHS. So what is the dimension of LHS? It is distance. So it is length. Isn't it? So we can write it is L. How many length are there? Only one. So it is L only. The power is 1. Isn't it? Then dimensions of RHS. Dimensions of RHS. So what is the dimensions of RHS? Here it is U. It is velocity. We have it is L T minus 1. L T minus 1. Then here it is time. So what is it? T plus half. Half it is a constant, so no dimension. Then acceleration, we already derived it. L T minus 2. Then what is it? Time. It is T square. So we can club this. Here first term we can write it in a single bracket. So it is L T minus 1 plus 1, isn't it? A raised to m into a raised to n is equal to a raised to m plus n inside the bracket plus L T minus 2 plus 2. So what is it? Minus 1 plus 1 is 0. So it is L T raised to 0. So it is 1. And here it is L minus 2 plus 2, it is again 0, only L. So dimension of LHS is L and dimension of RHS is L plus L, it is 2L. 2 again don't have any dimension. So we can write this 2L, 2 no need to consider. So what is the dimension? They are equal. Isn't it? So what is it? The given relation is dimensionally correct. Isn't it? The given relation is dimensionally correct. So here it is the one application of this dimensional analysis. Okay. So you have to write the dimension and check whether it is same. It is same here. So this S is equal to ut plus half at square is a correct physical equation. Okay, so we verified that on the basis of dimensional analysis. So the next question is, check the correctness of the given physical equation. V square minus u square is equal to 2as, half mv square is equal to mgh, and f into s is equal to half mv square minus half mu square. Okay, so the second one also, that is here, first one also I will explain you. The other two you do as the homework. Okay, so the what is it? A. Answer. First, what is the first step? Dimensions of LHS. Like your two quantities are there. So what is V? V, you know, it is the velocity, isn't it? Final velocity, and U is the initial velocity. And here A is the acceleration and S is the distance, isn't it? This is the equation you studied. So what you studied, that's only we are considering now. So velocity, we already derived that L T minus 1 square. So V square is that minus L T minus 1 square, isn't it? Whether it is the initial velocity or final velocity, dimension is not changing. So we can remove the bracket here. So what is it? L square T minus 2. Okay, minus L square P minus 2. Okay, then dimensions of RHS. Isn't it? 2 no need to write because it is a dimensionless constant. Then acceleration. What is acceleration? L T minus 2. Isn't it? Acceleration is L T minus 2. And S, what is the dimension? It is L. Isn't it? It is the distance, length. So here what is it? L into L. So that is L square, L raised to 2, T minus 2. So we can write it LHS as L2 T minus 2 minus L2 T minus 2 is equal to what? L2 T minus 2. See, don't subtract this, okay? We can't subtract it like subtract. So what is it? See the dimension. L2 T minus 2. L2 T minus 2 is equal to L2 T minus 2. Okay, so the dimension of LHS and RHS are equal. So the given relation is correct. Isn't it? So same way, find out mv square. Half no need to consider. So other two, B and C. Half mv square is equal to mgh. And Fs is equal to half mv square minus half mv square. You try to do yourself. Show that both side dimensions are same. Okay. So that is all for today. Complete your work, and the last application we will discuss in the next class. Okay. Thank you.